day to you all. Thank you for the honor of summarizing how to use delivered energy 5 times more efficiently by about 2060, or 3 times more efficiently by about 2040. Engineers would call this 5-eta, and it can make the clean energy supply side of global climate protection only half as hard as it looks today when we are exploiting less than half the solution space. The economic and security logics of both halves also favor distributed resources, and that produces good news. This doesn't mean any magic or miracle or new technology. It does need beginner's mind, whole system thinking, rigorously simple design, and meticulous attention to detail. And then to get it actually implemented, it takes gentle diplomacy and relentless patience. I'm going to sketch how integrative design can optimize whole systems for multiple benefits to achieve radical energy efficiency in all sectors. This proven practice, which my colleague Joel Swisher and I teach in winter and spring quarters, applies orthodox engineering principles, but it adds different design questions in a different order. It's the most overlooked part of the energy revolution that is rapidly shifting the world from inefficient to efficient use, fossil fuels to renewables, fuels to electricity, and centralized to distributed resources. Now, the result is the current tipping point. About 6 years ago, total use of fossil fuels posted onto a plateau and began bumping along through minor excursions due to weather or war. And right around now, carbon-free power is starting to beat all demand growth, and then more, even as electricity replaces more fuels. And all of that tips fossil fuels into steepening decline. Electricity, you see, has already taken all of the growth in final demand because fossil fuels peaked in industry in 2014 and in buildings in 2018. The light gray and dark gray visiting trends in net zero scenarios over at the right side of this graph are from Lindbergh and Energy Finance last year, but were similarly framed by the International Energy Agency, BP, Shell, McKinsey, Rystad, and others. And all of them said that the past 2 centuries of fossil fuel growth are now starting to reverse. We're right at the inflection point. Indeed, China's carbon emissions probably just peaked, mainly because over half its new cars are electric. China sells more electric cars than the US sells total cars, and China met its 2030 solar and wind target in the middle of last year, 6 years early, while India just did so 5 years early. In the US, this transformation was less driven by policy and climate than it was business-led, market-driven, informed by energy security and industrial opportunity. It's like many classic cascades of technology disruptions triggered by innovation and motivated by profit. Ember frames it this way as the electrotech revolution, which they put out a great new deck on 18 September. And it has these 3 synergistic technology clusters, but this framing includes only about a third of the total energy efficiency opportunity. And here's how, of 3 columns. At the upper left, the huge conversion losses in red from thermal power plants are eliminated at the lower left when solar and wind power in green generate directly without a steam cycle. In the middle column, fuel combustion at the top provides heat several-fold less efficiently than a renewably powered heat pump concentrating free low-temperature heat. And then in the right column, gasoline and diesel engines at the right, with their big losses in red, are far less efficient than renewably powered motors in battery electric vehicles. So across this whole bottom row, replacing fossil fuels with renewable electricity is 2 or 3 times more efficient in turning primary energy into final energy or delivered services. And that shift could save the world nearly $5 trillion a year, 5% of world GDP. But it does not yet include higher efficiency in the equipment being powered, or the building being heated or cooled, or the vehicle being moved. That's end-use efficiency, and it makes the heat pumps, motors, EV batteries smaller, cheaper, less mineral intensive. Both those kinds of efficiency multiply to form together primary energy efficiency. And most of its potential is in end use, where global efficiency can profitably rise by roughly 5-fold. In other words, about twice the upstream savings. That's why I said the conventional view only caps a third of the savings. IEA says that energy efficiency has delivered half of the past 20 years of decarbonization. It employs roughly 20 million people. It's investing about $800 billion a year, but its pace is now roughly 1.5% a year, and that needs to move to 4% a year or more to reach net zero by 2050. That's using the COP28 divide 130 target to double down with efficiency and triple up with renewables. IPCC's finding that efficiency can deliver 40 to 70% of future decarbonization is understated because it includes only technology and policy. I'll sketch how adding innovative design and the business model can make that efficiency resource several-fold larger. And that's why I mentioned quintupling global energy efficiency and use efficiency by 2060 at a pace within the aquifers of IEA's forecast range, and that's not limiting. A little history. Around 1975, U.S. government industry all said that the total input energy needed to make $1 of real GDP could never drop. A year later, I hermetically suggested it could drop 72% in the next 50 years. In the first 49 of those years, it dropped 65%, despite obstruction by disgruntled rivals. In the decade of 2018, the hydrocarbon industries outspent the clean energy industries by 27 times to influence federal legislation, and even more lately. Yet efficiency's potential, meanwhile, kept growing. Just the efficiency innovations already added by 2010 can save another threefold, twice what I originally thought, and a third the real cost. And today that's looking conservative because optimizing buildings, vehicles, and factories as whole systems, not as piles of little isolated parts, that often make very big energy savings, cost less than small or no savings, turning diminishing returns into increasing returns. When saved energy, about 2/3 due to smarter technologies, dropped U.S. primary energy use by 65% already, the cumulative savings were immense. Renewables, meanwhile, nearly tripled, but with 27 times less cumulative impact. Who knew? Renewables get virtually all the headlines because they're visible on rooftops and skylines, but energy is invisible and the energy you don't use is almost unimaginable. But much bigger savings await us, even as renewables are now over 90% of new generating capacity in the United States and the world. Worldwide, renewable electricity generation in green has zoomed past nuclear in magenta and gas in blue. It's about to pass coal in white. Indeed, solar output alone passed nuclear output in April and is adding 1 billion watts of capacity about every 12 hours. In the first half of this year, the world added more raw solar capacity than it has operating nuclear capacity built over decades. Modern renewables now look set to add more generation in 5 years than in the past century. And they've shifted energy from fuel extraction economics, the more you dig, the more it costs, to equipment manufacturing economics. So the more you build, the less it costs. It gets cheaper to capture free sun and wind. And already those cost curves of fuels and renewables have irreversibly crossed, triggering the exponential growth in the green curve. The Sam Freeman says the more we buy, the cheaper it gets. So we buy more, so it gets cheaper. And the resulting market competition will doom many fuel-based incumbents. So that tipping point already happened. Sorry if you missed it. Solar capacity is now blasting past every other global source of electricity, as you see on the left, while on the right, battery storage surpasses pump hydro storage capacity. So the world's adding about 80 gigawatts of batteries this year. The latest Chinese auction sliced another 30% off battery prices in June. They'd already fallen by about 95% in the previous 15 years. And for 4-hour storage, the Chinese packs are now down to about $51 per kilowatt hour capacity. Some Indian PV plus storage now sells for just $40 a megawatt hour, 4 cents a kilowatt hour. Investments in displacing fuel accounted 2 years ago for about 6% of total GDP in the United States, 21% in China, 30% in Europe, 4% in India. That's not counting their indirect stimulus for making energy service prices lower and more stable. And in the first half of this year, global renewables got $386 billion of investment. That's 138 times the $2.8 billion invested over the past 9 years in 12 startups hoping to make U.S. small modular reactors. The new energy reality is not linear but exponential. Here's the global growth since 2010 in generation by solar in gold, wind in aqua, electric vehicle fleets in dark blue, and installed battery storage in dark red. And this new normal clearly needs an agile mindset because it's hard to catch an exponential curve from behind. The U.S. shares in this rapid growth and is completing another record solar year, but it dominates the old energy industries, not the new ones. America is not the technological epicenter of clean energy as it was for the internet. That clean energy epicenter is China, where far-sighted policies built about half the world's renewable energy and even more of many of its supply chains. China's 7 biggest solar companies, which you may never have heard of, now contribute far more to the world's long-term energy supply than the world's 7 biggest oil companies do. They are all household words. China, Europe, and others with consistent long-term strategies will gladly grab any market where the U.S. falters, just as Europe already raised its renewable investment by more than the U.S. reduced its renewable investment. Just in May, to beat a price change, China installed in that 1 month 93 gigawatts of solar capacity plus 26 gigawatts of wind power. That's a gigawatt every 6.25 hours around the clock. We've never seen anything like this. And many developing countries are leapfrogging. For example, by 2021, Vietnam unexpectedly installed 19 gigawatts of solar power, including 9 gigawatts of rooftop solar installed just in the year 2020. 72% of that was in December, and it was mostly in the last week of December before a juicy feed-in tariff expired. You must not have gotten much sleep. It's like building half the nation's dominant coal output in 2 years. In Pakistan, in green, in the past 2 years, photovoltaics became the biggest power source and displaced a fourth of the utility supply. 17 gigawatts of Chinese PV modules were imported last year, 10 gigawatts in the first 4 months of this year. And Bill McKibben reports that a household solar system, 4 or 5 PV panels and a 3 kilowatt inverter, has become a routine part of the dowry for Pakistani brides. Both countries' grids and the utility business models are struggling to catch up with their citizens' entrepreneurship. Now, over half the world's new renewables are being installed in the global south, often at rooftop or village scale. Africa just added 20 gigawatts of utility-scale solar, plus unknown amounts on huts and in villages. Illiterate Indian grandmothers are becoming a core of excellent barefoot solar technicians. Such gridless speed could come to America. In late June, Jane Woodward took some of us to North America's biggest microgrid, just built by Redwood Energy in 4 months in Sparks, Nevada. They laid 20 megawatts of photovoltaics on the ground and then used novel power electronics and software to meld the world's biggest array of Second Life automotive batteries, about 800 packs each wrapped in a white tarp and set on cinder blocks, to form 62 megawatt hours of unified storage. Those old batteries provide anywhere from 2 to 48 hours of storage as needed for a few more years, then they get hot swapped and recycled. The result is a 100% solar, 24/7, 365 power supply, delivering 12 megawatts AC for on-site Crusoe modular data centers. More reliably than grid power, cheaper than its 8 cent a kilowatt hour price. So we don't need any more to guess or argue about which big loads will be built and thrive. We don't, we need to build a power supply until an AI data center is already mostly built, and then everybody can compete to build its supply. Solar microgrids are safe, silent, virtually water and maintenance free, zero emission, profitable, scalable. We're already designing something 10 times bigger than that, and if necessary, affordable. Another important accelerator is a new type of advanced transmission conductor from a U.S. firm. I advise we can pass this around if people want to play with it. Compared with ubiquitous steel core aluminum conductors, it doubles or triples the current capacity with half the losses, superior safety and reliability, and excellent economics. So this novel conductor can decongest many regional grids by simply reconductoring existing towers. This can often avoid a new right-of-way, greatly reducing cost, risk, and time. Just double that capacity reconductoring could nearly quadruple the U.S. transmission animal by 2035, according to a study at Berkeley's Haas Business School. And that would meet over 80% of the new interzonal transmission needed for 90% renewable electricity 10 years from now. And this product is better than that. So the three parts of the energy transition are that renewables will push out fossil fueled electricity, obedient electrons will displace fiery molecules, and efficiency will shrink waste, all at lower cost. But we've seen this movie many times before in steel, ships, road vehicles, lighting, power, heat, among many other sectors. Of course, the U.S. policy earthquake is now happening too, but I suspect that market fundamentals will prove more important, providing tailwinds stronger than policy headwinds. Uptake speed varies by location. RMI analyzed over 110 territories in the US and Europe and China, and most of them nicely fit an S-curve. Aggregated fit is even closer. About a fifth are leaders, a fifth are laggards, and three-fifths are chasing the leaders up the S-curves. All three regions are on track for about half solar plus wind generation 10 years from now. Non-hydro renewables' first trillion watts, first terawatt in 2017 took about 15 years to build. The next terawatt took 5 years at half the cost. The third terawatt took 2 years. The fourth terawatt, even less, it's due this autumn. And soon less than a year per terawatt. But that's only half the bigger electricity story. We are largely overlooking here a comparable or bigger energy source that may also be deployable quickly. That's the efficient and timely use of electricity. What could more efficiency plus renewables do together? Well, let's look at the efficiency side, because integrated design can more than double conventionally estimated potential energy savings yet at lower cost. How? Well, it's less by adding more technologies than by designing them out. And this basic paper explains how integrated design uses not more but fewer devices and not fancier but simpler devices, more artfully chosen, combined time and sequence. But those granular devices can be mass-produced with rapid learning, just like renewables. We're familiar with resources like copper ore bodies or oil reservoirs, finite and depletable assemblages of atoms. But energy efficiency resources are infinitely expandable assemblages of ideas whose use depletes only stupidity, a very abundant resource. For example, my wife Judy and I live in this house, farm, and office near Aspen, Colorado, 2,200 meters above sea level. Where the outdoor temperatures used to dip as low as minus 44 Celsius, with up to 39 days of continuous midwinter cloud. But our house does no combustion. That's sort of the 20th century. Super insulation, ventilation, heat recovery, and super windows that insulate like 16 to 22 sheets of glass that look like 2 and cost less than 3, make it 99% passive solar heated, 1% active solar. Eliminating the heating system subtracted more capital cost than efficiency added, reducing total construction costs. Saving also about 90% of the electricity, 99% of the water heating energy, and half the water did add cost, but all the savings together paid back in 10 months. Today, that would probably be less than zero. The secret is obvious. It's optimizing the whole building as a system, not the insulation or windows as a component. Often a building that costs less to build and far less to run depends on using expensive windows, because they're the most important step in eliminating costly mechanical systems. Our central atrium, shown here in a February snowstorm, has so far produced 83 passive solar banana crops. And without needing to look like this, our house helped inspire several 100,000 European passive buildings. Integrated design gives many benefits from each expenditure. So the white arch at the top of the upper middle image has 12 different functions, but only one cost. And an analogous approach works fine in, say, steamy Bangkok. Nearly everyone on Earth lives in a climate somewhere between Bangkok and Los Angeles. Progress in office buildings is illustrated by a series of green energy intensities and yellow energy savings scores. So Carbide's integrated design to retrofit the Empire State Building saved initially 38% of its energy, later 51%. With a 3-year payback, because smaller mechanicals paid up front for most of the efficiency. Now the owner hopes to raise the savings to 80%. A major energy service company also bid on that job. They offered a 3-year payback, but with disintegrated design saving 6 times less than we saved. Now much more than 6, more than 10 actually. 3 years later, our cost-effective Denver retrofit saved 70%, making this half-century-old federal complex more efficient than what was at that time the best new U.S. office. That in turn is only a third as efficient as RMI's passive net positive no mechanicals office near my home, using 1/9 the normal amount of energy. And this Bavarian building uses 2/5 less energy than that. And yet these technologies all existed over a decade ago. What mainly improved is not so much technology as design, the way we apply technology, but it's often left out. In 6 muggy Indian cities, kind of a Taiwanese pop, 1.5 billion square meters of integratively designed offices use just 66 kilowatt hours per square meter a year. That's 80% less than the Indian norm, with typically 10 or 20% lower than normal construction cost, but superior comfort and satisfaction. Glare-free lighting is delivered throughout these big floor plates by contract. If workers complain of glare or demand blinds, then the architect doesn't get paid. Zimbabwe's biggest office and shopping complex, Harare's Eastgate Center, with passive design inspired by termite mounds, uses 90% less mechanical energy to deliver the same or better comfort with normal construction costs and 20% lower rents. IPCC disproved the diminishing returns assumption by graphing decade-old European data showing cheaper energy savings toward the bottom and bigger energy savings toward the right for diverse building types and climates, as you see in the key at the lower left. Because new builds on the left and retrofits on the right saved up to at least 90% of their energy without costing more for you to save energy. So much for diminishing returns. There's a lot of vertical cost scatter. That just shows the business opportunity to conform inferior projects to best practice. Recent super insulation retrofits to net zero using a Dutch technique called energiestroom, like having a tea cozy around your house, and are also proving economic without subsidy.
Or when a big old Chicago office tower is doing a routine window replacement that saves nothing. A simultaneous deep retrofit we showed could cost even less and quadruple efficiency. Then inside buildings are further opportunities like the double efficiency vacuum insulated pots that I cook with, and a heat pump water heater from Switzerland with a COP of 6 with a 31 Kelvin lift or 15 with a 13 Kelvin lift. And buildings use half of global and 3/4 of US electricity. So both the building and the equipment inside are very important targets. So integrative design starts with the desired effect. Then to deliver it, you optimize buildings as whole systems, not a pile of disparate components. You pay for the efficiency by shrinking or eliminating building equipment, especially for heating and cooling. You save the most capital by applying efficiency from downstream to upstream, as I'll explain in a minute. You reward the design professionals for what they save, not for what they spend, and you optimize the sequence and timing of design steps. Here's the next game changer. It's a Princeton experiment that kept Singaporeans comfortable outdoors in a shaded, open-ended pavilion without drying, cooling, or substantially moving the hot, humid, still air. People were instead cooled radiatively by absorbing far infrared radiation from their bodies into vertical panels circulating 17-degree water separated from the humid air by plastic film. Cooling the panels to 20 or 23 or 25 degrees can thus deliver thermal comfort in 32-degree air with 80% relative humidity. The mild cooling that water needs can be done passively by special surfaces that selectively radiate infrared to the sky in any weather, even in the monsoon. And combining these passive technologies may provide tropical climate comfort in new or old buildings or in vehicles using no or almost no electricity. Perhaps a snap-together plastic version might be cheaply retrofittable into the world's apartment blocks and slum dwellings. Let's go try it. It may virtually eliminate long-term growth in the world's peak demand for electricity. What are we waiting for? Then there's industry, which uses half the world's energy and electricity, and where similar methods apply. For example, Paul Westbrook and I co-led the redesign of this Texas Instruments semiconductor wafer fab to use 40% less energy with 30% lower construction costs. So it was built in Texas, not in China. By 3 years ago, it had inspired cutting company-wide chip-making energy intensity by 70%, water intensity 62%, greenhouse gas intensity 72%, with further gains still to come. RMI's next wafer fab design showed how to save about 2/3 of the energy use and half the capital cost while replacing all 22,000 tons of electric chillers with any of 3 natural cooling methods that can give over 100 units of cooling with 1 unit of electricity. And on this campus, by the way, the Carnegie building uses passive methods to get that number to 50. And had Peter Rumsey been allowed to do the pumping part, it would have been over 100. Across diverse industrial sectors, RMI's $60+ billion worth of redesigns have typically found about 30 to 60% energy savings on retrofit, paying back in a few years, far better than the orange zone in the upper left corner, where most energy service companies deliver disintegrated design. In new factories, 40 to 90+% savings generally had lower than normal capital costs. And these superior results come from saving the materials industry makes, rethinking industrial processes, and redesigning basic elements like pump and fan and motor systems. I mentioned materials. Well, wonderful new kinds of low or zero or negative carbon cement are now emerging. So are smart ways to use less or cooler or cleaner process heat, including solar. But what should we do first? Start with demand. Need less, use other, use less, use longer, use again, align incentives. Only after minimizing need should we redesign production. So I looked around in the literature and found scattered but strong papers showing how smart structural design and new business models can profitably save at least half the world's cement and steel that now release 15% of global CO2. Better specification and application of concrete can save another twofold, together saving 3/4 of the cement before we adopt lower carbon materials or better production processes. Better structural design takes many shapes. Substituting tension for compression structures typically looks better, costs less, and uses about 1/8 the normal tons. Pouring concrete, say for beams, into curvy fabric forms, not rigid prismatic forms, can often save over half the concrete by putting strength and stiffness only where they're needed. And then the weight savings compound because you need less strength to hold up less weight. An airy 3D printed bridge can carry mainly its users, while massive concrete bridges support mainly their own weight. There's a 3D printed stainless steel bridge. Most importantly, floor slabs are about half the total weight of a typical mid or high-rise building. A 5 centimeter thick concrete floor slab corrugated like this picture on the lower left, can replace a 30 centimeter thick flat slab. And it costs less and it saves 3/4 of the cement and all of the steel. But then thin floor slabs plus passive energy design can save another 15% of core structural materials and 3/4 of the energy, while increasing net rentable space by a stunning 55%. How? Well, you see on the left, you design out that 1 meter vertical plenum at each story for the mechanicals and use thin slabs, and then you can put 3 stories with the same 2.8 meter ceiling height into the current height of 2 stories. Cost, complexity, and time fall dramatically. Once you see this, why would you ever build any other way? Next, what can we do inside factories that make this stuff? Well, half the world's electricity runs motors, half the motor torque runs pumps and fans. And engineers focus on those devices' efficiency, but often they forget that better pipe and duct design can save 80 to 90+% of the friction, 97% in my house. And if everyone did that, it could save roughly a fifth of the world's electricity or half the coal-fired electricity, typically paying back in less than a year in industrial retrofits and instantly in new builds. You see, in pipes, friction drops as nearly the fifth power of diameter, but cost rises as only about the second power of diameter. So we should use big pipes and small pumps. Fat, low-friction pipes make this little blue pump so small that it looks like somebody made a decimal point error, but with the fat pipes, that's all you need. And you notice that that pump is raised up to meet the pipe rather than conventionally dipping the pipe down to the floor and back up again with 4 elbows full of friction. Then on the right, the tan chillers normally would be in a neat row, but here they're staggered to eliminate remaining elbows when we lay out the pipes first, then the equipment. And yet such rearrangement of designers' metal furniture remains largely unnoticed, untaught, unpracticed. It's not yet in any standard engineering textbook or industry forecast or government study or climate model. Why not? Because it's not a technology, it's a design method. And few people yet think of design as a path to speed and scale. Probably no climate models even compete or compare efficient use with more supply, let alone look at this kind of design. At the Oakland Museum, our treasured Stanford lecturer colleague Peter Rumsey retrofitted an efficient piping layout that cut the pumping energy by 3/4 with a 2 or 3 month payback and eliminated 15 pumps that will never again waste energy and maintenance costs. Repiping another pumping loop and adding variable frequency drives doubled the flow and saved 85% of the energy. Peter simply asked the pipe fitters to lay out the supply pipes as if they were drains. Here's how most buildings pipe the cooling tower water back to the condenser. But if we lay it out instead the way Peter does, everything gets better. The only obstacle is force of habit. We should bend minds, not pipes. So I'm writing an illustrated guide for factory engineers called The Tao of Pipes. On Dal. Tenfold savings in, say, pumping may seem incredible, yet your heart at this moment is pumping blood about 10 times as efficiently as typical industrial pumping systems pump water. If your body's 100,000 kilometers or so of fractal blood vessels had the design and friction of standard industrial piping, you would need a heart bigger than your body. Very inconvenient. But your third of a kilogram, 1.5 watt heart suffices because your blood follows nature's standard design called laminar vortex flow. That's a whole other conversation about the other big design revolution, biomimicry, or innovation inspired by nature. Well, what do such savings mean for the pumps and fans that use over a quarter of the world's electricity? From the fuel burnt at the power plant to the end use, many successive losses compound. So only 1/10 of the energy in the fuel comes out the pipe as flow. But now turn those compounding losses around backward from right to left and they become compounding savings. So every unit of flow or friction you save in the pipe saves 10 units of fuel costs, emissions, and what Hunter Lovins calls global weirding back at the power plant. And as you go back upstream, the components get smaller and cheaper, reducing the total capital cost. So always start your savings downstream. Start at the end, with intent, with purpose. Do you even need the flow? Passive buildings and equipment will need less or no pumping. And while you're making the pumps, fans, and motors about 5 or 10 times smaller, because you fix the pipes and ducts first, you can also do 34 other things to the motor systems that collectively save about 3 to 5 times more energy than just the usual 2 improvements of high efficiency motors and adjustable speed drives. And they cost about 5 times less per saved kilowatt hour, because if you do the right 7 improvements first, you get 28 more as free byproducts. My team's 1989 systems analysis examined induction motors in red, synchronous in yellow, DC in green. Our system boundary was from the electric meter to the input shaft of the driven machine, but not counting anything further downstream, the machine and the pipes and ducts the loads. So altogether, we could cumulatively save nearly half the total 1986 US dry power energy, as shown in blue. Paybacks were typically less than a year at 5 cents a kilowatt hour. And this matches EPRI's estimated savings from that time, but it's twice those estimated now by IEA and a lot cheaper. So 36 years later, it's time to update and exploit this synthesis. Now let's apply the pumping system logic to big old data centers. 2/3 of the fuel fed into the power plant is lost to the plant and the grid. Half the metered electricity is lost to the cooling system and the uninterruptible power supplies before reaching the servers. Half the server energy doesn't reach the chips because it gets lost first in inefficient, usually very underloaded power supplies and lots of superfluous fans. Next comes severe underutilization of computing resources, mainly through insufficient virtualization. The resulting energy flow is about to disappear, so first let's magnify it so we don't lose it. Next comes sloppy bloatware, running many unnecessary threads and processes and making simple tasks very complex because compute cycles were cheaper than programmers' attention and someone else bought the energy, and maybe AI wrote the code. Downstream of all that, you may even have inefficient business processes. So in all, the red numbers at the bottom reveal that just a few hundred thousandths of the original fuel energy actually delivers customer value. Ouch. Where should we start fixing this? Start downstream. First, write elegantly terse code, optimally compiled, with the goal that every compute cycle is a needed and wanted one. I had assumed that this would save an order of magnitude in compute cycles, but recent tests found 2 orders of magnitude. And now that we've so much shifted to mobile devices, efficient code becomes valuable because it is stretching battery life. Well, then we can at least quadruple server efficiency, now even more. And the servers will need a lot less cooling and power supply, both doable in smarter ways. And we could even save half the utility losses by using fuel cell trigeneration, cheaper than the power supplies it displaces. So when you multiply these savings from downstream to upstream, you just cut the total energy use by at least 2 orders of magnitude. Now, we made this diagram, 16 years ago, and our client rejected most of our recommendations. So very disappointingly, we were only able to triple efficiency at the same capital cost. But our partner, EDS, Ross Perot's firm, said that had our recommendations all been adopted, we would have saved about 95% of the total energy at half the normal capital cost. So in May, I did this essay that Jan kindly mentioned on AI data centers, analyzing the risk that what increasingly looks like a multi-trillion-dollar bubble can put utilities and their customers at risk of a 12-figure overbuild that weakens finances and credit. Today's AI hype actually rhymes with a 1999 campaign funded by the coal industry to convince Americans that the internet would eat the grid without urgent construction of new power plants, especially coal-fired. Well, they overestimated the data center power use by about tenfold. But by the time investors woke up, they'd lost about $200 billion on hundreds of unneeded plants plus grid investments. Well, today, several firms that make up 30% of the S&P are betting about $3 trillion with a TR on new AI data centers implausibly hope to yield superintelligence, and they're subsidized by taxpayers in 36 states. The federal government's trying to mandate new data centers and their gas and nuclear power supplies under a national energy emergency, which seems to mean that those sources can't compete with renewables. So the gas, coal, and nuclear get boosted, renewables get blocked to try to reverse the market verdict. So all new data centers, only a fraction of them for AI, actually cause only about 5% of global electric demand growth. That might rise to 10%, but the supposedly exploding demand growth trumpeted in the US is actually not visible in national statistics, only in some local hotspots. And if it happened, it would be overwhelmed by renewable growth, as big tech prefers, particularly because the gas plants are far too slow and costly. Small modular reactors are not a thing, and they are even slower and costlier. And only the renewables that the federal government is trying to kill are fast enough to meet the AI ambitions they advance. So this contradiction may actually turn out to be good for climate because one of AI's biggest uses is making oil and gas production bigger and cheaper, perhaps raising emissions more than the efficiency gains reduce them. Nobody knows. It hasn't been rigorously compared yet. Now, many, if not most, new AI data centers are speculative, risky proposals that many analysts now consider a bubble or a potlatch of dumb money, one that could hazard the whole US economy because AI growth accounted for anywhere between half and all GDP growth in the first half of this year. And those data centers are big bets against a bunch of things. The order of magnitude gap between plausible AI revenues and needed repayments on that $3 trillion investment. The big risks that superintelligence will not emerge from the giant models, the hallucinations will not be solved, the small lean models and non-AI tools will continue to win for most uses, that depreciation will keep outpacing revenues, and that actual uses that provide net value to the user are proving to be quite rare, about 5% in several recent surveys of general business use. Now, meanwhile, better hardware and software and system architecture are about quadrupling AI electric efficiency each year, with about 1 million-fold to go. So to use and pay for the same amount of electricity, a data center would have to quadruple its service sales every year for decades. Google is also already selling to utilities the data center operational flexibility, a very small amount but very valuable, that makes new power supplies unnecessary. It means all the proposed data center growth in the US could be met by existing utility assets. Another competitor would combine an existing gas plant with renewables, storage, and a data center. And often the best buy will be efficiency and renewables on-site or elsewhere, like Redwood Energy's 4-month pop-up solar microgrid you saw earlier. So that altogether, that's an awful lot to bet against. And if the developer loses any of those bets, other electric customers should not be stuck with the bill. So I've therefore suggested in recent articles a take or pay power contract to pay off the power supply investment, backed by a bond or insurance policy to protect other customers or investors from a failed data center project. And then the risk is priced by independent risk management experts in the capital markets, and it's charged to the developer who hopes to profit. I think those conservative economic principles make a lot of sense. So that's the short story on AI data centers. What about transport? Well, 2/3 of the energy needed to move a typical car is caused by its weight, and only about 0.3% of the fuel energy actually moves the driver. But ultralight, ultra-strong materials can slash energy use and improve crash safety. BMW made money on each of 250,000 i3 EVs, including mine, by making it out of costly carbon fiber that was paid for by needing fewer batteries to propel the lighter weight car. Fewer batteries also recharge faster and need less electricity and less infrastructure. EPRI said this could potentially save the US about $200 billion a year. The saved weight snowballs spectacularly. Assembly saves 2/3 of the normal capital and water and half the energy, space, and time at the auto plant. It eliminates the 2 hardest steps in automaking. It's much better for workers. The car's quadrupled efficiency is uncompromised with many driver advantages. And this and 14 other empirical examples show that the design space for efficient autos is at least 3 times bigger than officially assumed. Ultralighting can also save up to about 2/3 of the scarce battery minerals. Then there are 5 other multiplicative forms of efficiency that can manage the rest. Meanwhile, Bloomberg reports that China's strategy for its 2030 flagship cars aims to displace 4/5 of their iron and steel with carbon fiber structures. Watch this space. The next game changer could be a couple of hypercars from small firms I advise now finishing their production capital raise. Most drivers will not need to recharge this American carbon fiber 2-seat 3-wheeler or this Dutch metal 5-seat 4-wheeler because they're both about 3 times as efficient as a Tesla. So their topside solar cells capture enough energy for ordinary daily driving without plugging in, bypassing the charging infrastructure and its electricity supplies. Thus, oil has become uncompetitive even at low prices before it became unavailable even at high prices. But that's not only about autos. Tesla's battery electric heavy truck is being customer tested for mass production starting around year end, and it will triple to sextuple the big diesel 18-wheeler fleet efficiency with great economics. Then there's this thoroughly flight-tested air taxi that could fly nonstop from San Francisco to Dublin with 1/8 the fuel use of a normal business jet. A mid-sized hydrogen model has been announced, plus importantly, a transonic business jet for 2030 service with doubled efficiency and doubled cabin size. The superlaminar aerodynamics can scale to probably 737 size and could blow up aviation's business models. Or metal aerostructures could be replaced by 98% lighter polymer film and lattice structures. Other proven improvements could be added to let my grandsons ultimately fly all solar airliners across the Pacific. It's the EV story 25 years later. So across all sectors, the summary shows the immense end-use energy efficiency potential, not counting the tripling before that of potential primary efficiency upstream. And my posted lectures give hundreds of examples. But this 5/8 potential is seldom recognized, taught, delivered, expected, rewarded. The same design errors you see are common in our textbooks in our classrooms. So I'm hatching a plot for, to put it a little impolitely, the nonviolent overthrow of deficient engineering. Teaching disintegrated design condemns our descendants to perpetual retrofit of inefficient stuff. That's not a worthy legacy. To help us be good ancestors, I'm seeking fellow students, teachers, and practitioners to collaborate on making integrative design move swiftly from rare to common. I think all this implies that demand growth for air conditioning, electric vehicles, data centers, industry can be modest if best practice spreads rapidly and if efficiently is fairly competed or compared with marginal supply. Then a prosperous, fair, climate-stabilized world would need far less generation growth than usually assumed, perhaps still less grid growth because economics and security, as described in a couple of our previous books, favor distributed resources for most uses. Then we won't need speculative, slow, costly technologies like nuclear fission and fusion, except, of course, the well-engineered, remotely sited free fusion reactor already thoughtfully provided and cheaper to harvest than to replicate. Buying cheaper, faster efficiency renewables instead will displace more fossil fuel per dollar and per year, and thus make the Earth's climate more stable, not less. And yet we are often told that we need thermal power plants to complement supposedly intermittent and unreliable solar and wind power with clean, firm power. I think this is economically nonsensical because thermal plants following net load after dispatching cheaper renewables would have even lower capacity factors and less competitive costs than they have now that cannot compete. But it also overlooks modern grid integration experience because variable does not mean unpredictable. Here's how accurately the French grid operator in a stormy winter month a decade ago forecast a day ahead the actual output of the country's wind farms. They would do well to forecast demand that accurately. To keep the grid reliable as it becomes renewable, we also have at least 10 carbon-free ways, conceptually sketched here, to balance the grid across all timescales, not just big batteries in magenta, and without needing fossil fuel backup in red. Your actual costs will vary, but bulk storage is not the only method, and it's now moving leftwards towards a medium cost range. So we don't need to wait for a storage miracle, although some are emerging, partly at Stanford, and the market isn't waiting. The first 2 boxes on the left, megawatts and flexawatts, timely use, are both several-fold bigger than had been thought, but cheaper. So giant batteries are valuable, they're profitable, they work fine, they're able to get global power most of the way to net zero, but they seldom look necessary. To see why, consider Texas with a 99% isolated grid, no big hydro, but a 2050 summer week of expected loads can get a lot smaller and less peaky with very conservative estimates of profitably efficient use. Well, then we could make 86% of the annual electricity with a combination of wind and solar cells, and another 14% from dispatchable renewables, of which my favorite is burning obsolete energy studies. And then you've got 100% renewable supply, but you can see it's not a great match to the load, the dashed line. So to match them up, let's put surplus electricity into two kinds of distributed storage worth buying anyway: ice storage, air conditioning, and smart bidirectional charging of electric vehicles, and then recover that energy when needed and fill the last gaps with unobtrusively flexible demand. Well, now we've got 100% renewable electricity every hour of the year with no bulk storage and with only about 5% left over to help decarbonize other sectors. So the economics should be excellent, even at today's prices. What about the infamous dark doldrums of Central Europe? Well, the 99.999% reliable, 73% renewable last year German grid operator 50 Hertz, targeting 100% by 2032, has capably analyzed how, with east-west interconnectors, the Dunkelflaute would need backup power for only up to 1 or 2 weeks per year, totaling just 6% of winter use. So that needs only existing gas-fired capacity burning green molecules like hydrogen or ammonia made at other times from surplus solar or wind. So the often claimed need for months or seasons or years of storage was not found. That's partly because this study, unlike most, included more of our 10 solutions. So it included moderately efficient use, electric vehicle integration, heat pumps, behind-the-meter home batteries, and demand response that by itself could cut the under or over supply days of renewables by 90%. And some grid operators are doing these kinds of choreography today. Here are a few examples of how much of electric needs in various European countries were met renewably in a recent year. And these places generally added no bulk storage, and they're meeting half, 3/4, or more of their annual electric needs from renewables with superior and rising reliability. For Germany and Denmark, it's over 5 times as good as ours. And a couple of years ago, 60 countries or territories were already at least half powered by wind, sun, and water, 12 of those at least 98%. 11 US states were 53 to 118% renewably powered and often had some of the nation's lowest electricity prices. So as my colleague Clay Stranger puts it, these operators have learned to run their grids the way a conductor leads the symphony orchestra. No instrument plays all the time, but the ensemble continuously makes beautiful music. And one of the most beautiful examples now is the gigawatt scale grid of the state of South Australia. The operator expects to complete the transition to 100% solar and wind net generation. They have no hydro in 2027, 2 years from now. So the upper graph shows the past 25 years of the monthly consumption mix. Solar in yellow and wind in green have pushed out coal in 2016, that's brown, some imports in purple, and pushed out most of the gas, the light and medium orange, with very successful and lucrative stabilization by big batteries and 4 fuelless synchronous condensers. Last month, the state started running with just 1 gas turbine, occasionally 2, as the only synchronous generator. That's because the regulator said to, not because they think they need it. And it's producing the minimum output of 40 megawatts. That's 2.4% of total supply. The lower graph shows the dramatic reduction of power sector carbon emissions, soon to be profitably eliminated. So now 37 big companies want to come build factories in South Australia to use this affordable, stably priced, reliable green power. If they all did that, it would increase demand by tenfold. Nice problem to have. This matches Rio Tinto's choice of solar and wind as the main power for its new aluminum complex, Apple's 4 renewably powered data centers, Pentagon's preference for renewables to power its most critical missions, and so on. Most of the climate choice and electricity forecasting models that now drive global policy have big flaws, particularly the three I've put in color here, like assuming that renewables will cost a lot more in 2050 than they actually cost in today's market. Fixing these problems could, of course, change the results, although academics would be deprived of many things to argue about. And there's a very important Oxford paper a few years ago that transparently extends the argument with a simple but powerful way to understand why the energy transition gets cheaper as it gets faster. Real energy costs for up to 140 years in the left-hand graph have long been about flat for fossil and then for nuclear energy, but steeply declining for major renewables, which kind of did a meteorite strike on price and drove the unprecedentedly rapid growth in the second graph. Notice these are both on logarithmic vertical scales. And yet virtually the entire literature is unmoored from the observed power prices. The inset histogram in the third graph shows that nearly 3,000 model runs predicted solar power costs in 2010 to 20 would fall by a mean of 2.6% a year. The highest was under 6. The actual cost drop was 15% a year. The most optimistic renewable forecasts in those models were the IEAs, which are shown in the third graph as colored lines coming off, assumed far lower cost drops and hence far less solar growth in the decisive next decade. And the fourth graph shows how the economic theorists then assumed those green lines as absolute cost floors that solar could never get below. Well, it cheerfully blasted through them one after another, and it's still doing so. So these models are based on economic theory, not engineering practice. And today they continue to drive global climate policy and hence climate reality by insufficient ambition. Last graph. How much electricity the world will need is unknown within a factor of 2, at least I would guess upwards of a factor of 4, but it's not fate but choice. Will electrifying everything make demand double, quadruple? Well, I would like to start by understanding Norway better. It has the world's highest EV market share. This summer it was 97%. Norway's 2024 car fleet was 28% battery electric and another 7% plug-in hybrid. By 2020, 60% of Norwegian homes had shifted to triple efficiency heat pumps. And over the 33 years shown, 1990 through 23, real GDP rose 105%. How much did total annual electric use go up? 24%. What's going on here? Well, to conclude, climate science models are conservatively understating the speed and the runaway potential of climate change. Models of climate choices and consequences, at least as conservatively, are understating what we could do to stop climate change. Offsetting those two contrary biases, the race of our lives, the race for our lives, is very much odd. The outcome is up to each of us, and despair and complacency are equally unwarranted. Our responsibility is to enable the new energy system, not protect the old one. So the energy transformation can move at the pace and cost of design and software, not of infrastructure, and can be not constrained by the inertia of incumbents, but sped by the ambition of insurgents, like many of you. Just remember Marshall McLuhan's remark that only puny secrets need protection. Big discoveries, he said, are protected by public incredulity. So how incredulous are you? I'm eager to hear what's on your minds. Thank you. I'm sure I said nothing controversial.
Any questions from students first?
Please.
Why do you think free data centers and AI companies are not
Oh, some of them are designing good stuff, and the main builders actually do prefer renewables and have already bought a great deal of renewables and would like to buy more. But there are a lot of lower quality projects, a lot of companies that don't have the best designers or aren't asking the right design questions. And the market will sort them out, and a lot of people will lose their shirts and deserve to. Well, competition's a pretty good way, and there's probably some good shorting opportunities. It's pretty clear what the direction is for a lot of these projects, and you can probably sniff out which are speculative and risky. The timing is harder to predict, though. So often these things last longer than you expect them to, sir.
Last year we're looking on ability to see regulation related to data center growth. And I was just wondering, it seems that the utility and it's very conservative about these kind of ideas that you really. I'm wondering to what extent you think, like, it's a regulatory thing that's something that's blocking the like path for like a lot of any when it comes to data centers versus is it some other like what is it regulatory versus?
I don't think, well, Joel can help me on this. I can't think offhand of regulation that is blocking efficient data center. There is some federal policy at the moment trying to push uneconomic supply that couldn't compete in the market as the mandatory supply for new government-sponsored, government land, et cetera, data centers. And those will probably, well, they may meet the fate they deserve, but they're not in the market, and they may simply be socialized waste, and we'll see how they do. But I think state utility regulators are a key source of rationality, and that's why I summarized my essay with particular emphasis on regulatory opportunity in Public Utilities Fortnightly, which all the regulators read, and in Utility Dive, which most people in the electricity industry read. And that's getting some attention, and I'm hoping to get something into the bond buyer in the hope that people who develop financial products will develop some bonds to back the kinds of take-or-pay contracts that I believe Indiana and maybe it's Tennessee, I forget, 2 states now have actually adopted for data center projects. They just need to get the insurance or bond product into the market to back the take-or-pay contracts, and then the other customers will be protected from irrationally exuberant power plant proposals.
Let's give another round of applause to Emeritus.
Thank you.
2 gifts to you. One is a jacket for Bits and Watts.
Oh, wonderful.
One
Thank
is
you.
a new report we just released with Will and Aaron Price. We together called the Power AI at the Speed of California.
Good.
We echo your concept regarding take-or-pay, regarding need for flexibility, regarding the co-location for clean electricity as well. So.
Yeah, thank you. Well, let's let this and things like Redwood Energy's 4-month pop-up compete.
We can have offline conversation, but I want to understand how many batteries they deploy there.
About 800.
800 versus solar.
Well, let's see. It was 20 megawatts DC of PV modules on the ground, about 800 packs, which in aggregate, combining all different shapes, sizes, chemistries, came out to 62 megawatt hours of storage. And that's enough for completely solar all the time at under 8 cents a kilowatt hour, which is the grid price. Now, they're producing for less than that. They're not saying how much less, but I think they're making a good deal of money on it.
Very good. Thank you, Emerick.
Thank you.